Well, hello everyone. This is Mr. Minnick, and today in stats class, my absence is because I'm at a meeting. My sixth period class might or might not watch this back. I don't know. We'll see. But anyway, we're taking a look at Chapter 5 now. In this first section of Chapter 5, Section 1, the topic for discussion is discrete, and we've talked about a lot of these words already. It's just a matter of putting everything together. Um, Discrete random variables. Hey, we've talked about variables before, and we've talked about discrete before. So, like I said, like I just mentioned, a lot of this is just a combination of things we've studied, and probability distributions. Probability distributions. Okay. So Chapter 5, Section 1, discrete random variables and probability distributions. So we've been in school for a while now, 20 some weeks, maybe about 25 weeks, give or take. So you know the drill. There probably will be some kind of essay test or written test or quiz over this material. So taking notes, as always, would be a good idea. So let's talk about a variable for a minute. Remember what we said about a variable in the context of statistics is it's something that describes something. Okay, that's kind of vague. It's a characteristic. It's a characteristic about a subject that varies from one to the next, or can vary from one to the next. Okay, so for instance, let's suppose our subject is cash, money, paper, bills. Okay? So that's our subject, cash, money, paper, bills. You open up your billfold or your wallet or your purse, or you go to the bank and you get your paycheck, or you, heavens forbid, you rob a bank and the bag's got all kind of money in it. Um, so, so a variable then, relative to the subject, the variable could be, and here's several of them. The variable could be the worth. How much is it worth? Is it a $1 bill? Is it a $5 bill? Is it a $10 bill or a $20 bill or 100? Those new hundreds are funky looking. Maybe it's the serial number. Okay. Maybe it's the number of safety features. You know, a friend of mine back in high school did a research paper. If any of you are looking for a topic, it's a pretty neat topic. Money and how the government tries to safe-proof money. There's a lot of safety features on dollar bills. Back in the 90s, they put that stripe in them, and I actually worked with a guy who could pull that stripe out of them without damaging the dollar. But anyway, how many safety features are on the dollar bill? So hopefully you get the idea of what a variable is, and then what, well, let me just kind of stop for a second. Variable, worth, let me highlight that, worth, serial number, number of safety features. Each one of those variables has a finite, now you might think serial number, well, serial numbers can be pretty lengthy. You're right, they can. But each one of those has a finite or a measurable or a countable or a listable. That's not a word, listable, but we could list all of them. We could make an exhaustive list of the worths of a dollar bill, of the serial numbers of $20 bills, let's say, or of the number of safety features. There's probably not that many safety features, okay? So when you hear the word discrete, that's kind of what we're talking about, okay? So we'll get a couple definitions out of the way. So definition, random variable. Random variable. The definition is this. It's a quantitative. It's a quantitative. Remember, quantitative doesn't just mean numbers. It means numbers that it makes sense to total them, to average them, to make computations with them. So a quantitative variable, a quantitative, that is a Q, a quantitative variable. And here's the interesting part, and here's where it's random. Whose value depends on chance? Whose value depends on chance. Okay? So if we randomly pick a dollar bill, we don't know what it's going to be. There's a certain chance that it's going to be $1. Okay? If it's my wallet, there's a greater chance that it's going to be $1. Whoa, what happened with quantitative? This is a quantitative. Let's try that again. I can spell today. Let's try that one more time. A quantitative. There we go. That should work. So a random variable is a quantitative. In other words, it's numeric, and it makes sense to add, subtract, total, average those numbers. So it's a quantitative variable whose value depends on chance. Does it make sense to average the dollar bills? Well, it might not make sense to find a mean because there's no such thing as a $2.50 bill. But it would make sense to find the median or to rank them. Okay, so it depends on chance. Okay, that's where the randomness comes from. So just some other examples of random variables. Examples. Everybody loves puppies. I don't understand why. They stink and they have worms, and that's really nasty. And because of that, I don't think I'll ever own another dog that I get as a puppy. I couldn't eat spaghetti for a long time. I know that's gross, so I'll shut up. So examples. The number of, notice it's the number of, how many? The number of puppies in a litter. It's a chance. Maybe there's 2. Maybe there's 19. I don't know. I don't know the science or the biology behind dogs and their reproduction, but I do know that with puppy litters, it varies. It's chance. Okay. Another one might be, and I'm not into the stock market because I don't have enough money left over because I spend it on other things, but the return on an investment. Okay, you take fat stacks of cash, you take $5,000 and you invest it into the market. What is your return? Well, it's going to be a dollar amount, hence quantitative. It's going to be a dollar amount. And it's chance. Okay, if you invest in oil, chances are you're probably going to get a return on it. If you invest in something else, who knows? It's totally chance. Okay, another one would be the lifetime of your cell phone battery. Okay? Huh, yeah, that's why I'm charging it now, because the stupid thing's dead. Well, it's totally chance. Well, it's actually not totally chance. The more apps you have running, obviously, and the colder it is, the more that would die. So, all right. So that's the definition then of a random variable. Like I said, your cell phone battery, well, they don't last so long. You can buy high capacity batteries, but obviously you're going to pay a little bit more for them. So our next definition then is for a discrete random variable. Now, discretion in this context doesn't mean what it normally means. Okay? Normally you see discrete and you think, oh, let's be discreet about this. We're going to be we're going to be at my parents' house, and I don't want them to know that we're engaged and that we're going to be getting married. So let's be discreet. Not that kind of discretion, okay? Discretion in this context means it's finite. It means you can't have an infinite amount. There's not an infinite amount. There's a listable amount. And I said listable is not a word, but it's a random variable where whose possible values, a random variable, a random variable singular, whose possible values can be listed. A random variable whose possible values can be listed. I love milk, okay? Can't stand the 1%. If you drink 1%, good for you. I can't stand it. It's got to be the red milk for me, okay? But suppose you buy some milk, okay? So a random variable might be the size of the milk container that you buy, okay? Size of milk container. Depending on where you're at, the sizes will vary. What do you mean by that? Well, in America, we use the standard measurement. We get that from our English ancestors. I think it's silly. Um, so you buy milk, okay, and it might come in a pint container, okay. So that would be one of the first sizes, okay. The next size then might be a quart. It's possible to buy a quart of milk, okay, and then you could buy a half gallon. Usually we buy milk in a gallon. Some places I'll bet you could buy a 2-gallon container of milk. Some places I'll bet they might even make a 5-gallon jug of milk. Heck, they might even make a 20-gallon keg of milk. Okay, wouldn't that be weird, going to a kegger with milk? I don't know. Okay. The point is, you could list all these. Okay, so you go to the store. Well, they don't have the pint. They have, well, a pint's a half of a quart, and a quart's 32 ounces, and a pint's 16 ounces. In school lunches, they have 8 ounces, so a half pint. Okay, well, pop bottles. Maybe they put milk in pop bottles. Why? I don't know. But maybe it's 20 ounces. Okay, maybe they go with this weird size, 24 ounces. Okay, that's kind of weird, but they could. The point is, you could list all the possible milk containers. Even if we went to Europe and we started to buy milk in Europe, you could probably get 1 liter of milk, okay? Or you could probably get a half liter. Notice I use decimals because that's how they do with the metric system. A half a liter of milk, okay? You could probably get 3/4 of a liter of milk. And I think it's kind of ironic that with the metric system, they actually split it up into fractional parts, but that's a whole other story. Anyway, the point is, regardless of all the different kind of milk containers out there, you could list all the possible ones. So that's what we mean when we say discrete, okay? So a new idea, something that we haven't studied yet, is the notation for random variables, okay? For regular variables, we use lowercase letters. However, to represent random variables, we use capital letters. Okay? To represent random variables, we're going to use capital letters. Same letters as normal apply. Okay, so usually we use X. We're going to use X. Some people have siblings, some people don't. So let's suppose, for instance, that our random variable denoted by capital X is the number of siblings you have. Okay, so the notation that they use is kind of weird. Let's suppose you have 3 siblings. Suppose you have 3 siblings. If that's the case, we need some way to notationally represent that. So, notationally, the event you have 3 siblings, where the variable X is the number of siblings, where the number of siblings you have then is represented by the variable X. The event you have 3 siblings is represented using this notation. We say, and we use braces for set notation, capital X equals, end brace. I forgot the 3. 3, end brace. Okay? So the event you have 3 siblings would be represented using this notation. It's kind of weird notation, but it will show up on mathexcelforschool.com. Okay? You will be asked to use that kind of notation on mathexcelforschool.com. Okay? Now, if you had to read that out loud, it would simply be read as x equals 2. Or x equals 3, I mean. X equals 3. In this context, what it means is the event x is the random variable how many siblings you have. And in this particular instance, right here, I have 3 siblings. Okay, that's what that means. And if we're talking about probability, we use, obviously, the capital P. Okay. So maybe you're asked to find the probability that someone has 3 siblings. And if we were asked to find that, we would say the probability that someone has 3 siblings, and that should be a capital X, got to be real clear on that. The probability that someone has 3 siblings is, okay? So literally translated, this P here means the probability of, and then this means someone, or you, having 3 siblings, okay? So hopefully that notation makes a little bit of sense. I think what I'll do at this point is go ahead and log into Math Excel and take a quick look at 1 or 2 of the exercises from this section, just so we can see how that would go then. So like I mentioned before, really we're not doing anything new here. Just some of the notations a little bit different. Okay. Just some of the notations a little bit different. So at this time, I'd like to give shout outs. I'd like to give shout outs to Ale. Shout out to Mr. Englehart for watching my class. Hopefully they're being okay for you. What about the rest of us, Mr. Minnick? Don't we get shout outs? Well, Brown and Brown too, they get shout outs. They know who they are. And Nate Pinson's in the back saying, what about me? I thought you loved me, Mr. Minnick. Well, I do love you, Nate, so you get a shout out too. Everybody else is saying, well, what about us? Don't we care? Don't we matter? Well, sure you do. So shout out to the whole 4th grade class. So this internet's going to take a while to load. The computer's going to take a while to load. So now we probably ought to look at distributions and histograms and what the differences are between them. Okay, so we'll define them, and then we'll come back to the computer here in a minute. So a probability distribution. Probability distribution. The definition of a probability distribution is that it's a listing. It's a listing of the possible values a probability distribution is a listing of the possible values and corresponding probabilities and corresponding probabilities of a discrete random variable. Of a discrete random variable. Or a formula for the probabilities. Or a formula for the probabilities. Okay. So that's the definition of a probability distribution. Now we've made something similar to this in the past that's really the same thing. It's not quite a frequency table, but it's real close to a frequency table. It's actually a frequency table relative to everything in it. So it's a relative frequency table is essentially the same thing. So if you think about it, let's look at number of siblings. Okay, X number. That was a weird looking end. The number of siblings. Okay. Now I know there's one or two of you in this class who have several siblings, but for sake of simplicity, we're just going to say all the possibilities. All the possibilities for the amount of siblings you have. Maybe you're an only child. Maybe you don't have any siblings. You have one or two or three or four. I think there's one of you that might have more than that. Okay? So rather than saying the frequency and then the relative frequency, though, we just simply jump right to this. We jump right to the probability. Okay? The probability. The probability that the random variable x equals x. Okay? So it's weird because this x here is a little x, this x here is a little x, but the other one there is a big X. Okay? So as far as numbers in this table, remember this is by chance. It depends on what group of people or things we're looking at. Wait a minute, things don't have brothers. Well, sometimes things do have brothers. 0.200, 0.425, 0.275, 0.075, and 0.025. If you look at that and try to interpret that table, it's saying, you know what, there's a greater chance that you have one sibling than there is you have no siblings. There's a greater chance that you have 0 siblings than you have 4 siblings. You have the highest likelihood of having just one sibling. Okay? If we took this poll 60 years ago in an Irish Catholic home, I'm sure the results would be different. Okay? I'm sure that the column for the number of siblings would have to be increased a lot. Okay? But for this particular instance, we're just including the possibilities: no siblings, 1, 2, 3, or 4. Okay? All right, so a probability histogram then, our next definition, a probability histogram, probability histogram. We've seen histograms. Remember when we had a relative frequency table, then we made a relative frequency histogram? Well, a histogram is simply a graph. It's a graph. It's kind of like a bar graph. It's a graph of the probability distribution of a probability distribution. If I was smart, I would have cloned the word probability and just kept on cloning it or pasting it because it comes up a lot. But it's a graph of a probability distribution that displays possible values. That displays possible values of a discrete random variable. A lot of writing here. Of a discrete random variable on the horizontal axis. We're about halfway done. And the probabilities, and the probabilities, and the probabilities of those values on the vertical axis, of those values on the vertical axis. The probability of each value, a new sentence, the probability of each value is represented by a vertical bar. The Probability of each value is represented by a vertical bar whose height equals the probability. Whose height equals the probability. Okay, let me put that full screen so everybody can see the whole thing. Probability histogram. Histograms are graphs. It's a graph of a probability distribution. So chances are in the homework, once you have a probability distribution, one or two questions that follow it might ask you to identify the histogram. Real simply, you're just going to look at the bar graph, look at the probabilities. Greater probabilities will correspond to greater heights of the bars. Okay, so along what normally we think of as the x-axis, in each bar will be each of the discrete values, each possible value for that particular variable. The heights of the bars will correspond to probabilities. Probabilities, remember, are between 0 and 1, so the heights are never going to be greater than 1 for any individual category. Okay. So hopefully Math Excel is ready for us now. If it is, we'll go ahead and take a look at that. And then really there's just one more idea after that we need to talk about. Other than that, I have no doubt that you'll be able to figure out the homework. Okay. All right. So Math Excel says, well, we need to connect to the internet. Says I need to enter a username. Let's try this again. Well, we don't want to do pre-calculus. Well, Mr. Engelhardt might want to do some pre-calculus. I actually wouldn't mind looking at some pre-calculus, but we're going to go to statistics. We're going to go to the 5.1 homework, and we'll take a quick look at it and see what's going on. Preview, here we go. Going to try. Is it going to load? All right, okay. The following table displays a frequency distribution for the number of crew members on each shuttle mission over a 10-year period. Let X, so X is a random variable, it's going to denote the crew size. So how big's the crew on a randomly selected shuttle from this time period? So crew sizes range from 4 to 8. Crew sizes with 4 members, it happened twice. Crew sizes with 5 members happened 7 times. Crew sizes of 6 members happened a lot more than anything else. Crew sizes of 7 members happened 21 times. Crew sizes of 8 members happened once. So it says, what are the possible values of the random variable X? Well, what is the random variable X? Well, it says it's the crew size. Well, what are the possible values? Well, there are 4 and 5 and 6 and 7 and 8. And that's it. Check answer, and we're excellent. Good. Now notice the set notation. It says use random variable notation to represent the event. So we're going to use a capital X. Got to be a capital X. The event that the shuttle mission obtained has a crew size of 7. The random variable crew size, X, is 7. Good job. If I had used a small x, it probably wouldn't have given me the right answer, okay? Moving along, find the probability that x equals 5. Okay, so this is where you're going to need a calculator. You'll need to find the sum of the frequencies, because that'll be the total number of crews that have gone up to on this shuttle mission. And you'll need that total, and you'll have to divide the frequency in the category for 5. You'll have to divide 7 by that total. Okay, so hopefully you get the idea there. So what we'll need to do then Let's talk about one more idea. And once we talk about that, I think you'll be in good shape. Last idea we need to talk about is this. If we were to add up all the probabilities, the sum of the probabilities of random variable x equaling of random variable x equaling x. In other words, we add up all those probabilities. The sum is always going to equal 1. If we go back to our table with the siblings and we added up the 200 thousandths, the 425 thousandths, the 275 thousandths, the 75 thousandths, and the 25 thousandths, if we add that all up, the total each and every time has got to equal 1 because that should be an exhaustive list. So that's basically it. It's been real. It's been fun. You tell me if it's been real fun. I will see you next time.
Good.